Hi, for our project, we did a residential geothermal cooling system design.
I'm Bodie.
I'm Carey.
I'm Diane Kohlin.
And I'm Ryan Moser.
And we are Group 8. The purpose of the research conducted was to design an optimal geothermal cooling system for a generic house. Geothermal heat exchangers are a form of thermal regulation which rely on the environment rather than the fossil fuel. A geothermal heat exchanger works by running water underground, which maintains a constant temperature of 50 degrees Fahrenheit in the Midwest. This allows for water to either be heated or cooled in a secondary heat exchanger system and brought back to the neutral temperature of 50 degrees Fahrenheit for only the cost of pumping. A geothermal heat exchanger used in regulating home temperatures have essentially 3 total loops. The water loop, which travels underground, the refrigerant loop, which utilizes a compressor and an expansion valve, and finally the house air duct loop, which transfers the heat from the refrigerant system to the home. The focus of this project will revolve around the analysis of the water ground loop heat exchanger system and how it interacts with the refrigerant system. The size of the house for which the geothermal heating system was designed was a 2,000 square foot home of 1 story. It was learned through research that the average house requires 20 BTUs per square foot per hour to maintain a constant temperature. For our system, this led to a requirement of 40,000 BTUs an hour, giving us the necessary heat exchange rate. This also converts to 11.72 kilowatts, which will be used in calculations. The 1 acre plot was selected as the average amount of land for a house of this size. A sizable chunk of land was also required for the length of the pipe necessary. The soil in the Midwest is saturated clay, which has a thermal conductivity of 1.5 watts per meter Kelvin. The pipe will be buried and thermal flux can be calculated relative to the length of the piping network.
The piping layout chosen was a horizontal pattern buried at a depth of 5 feet. In order to minimize the area required for the ground loop, the pipe was arranged in a series of U-shaped runs, leaving 5 feet between parallel pipes. The overall area required by this setup is a rectangle 95.5 feet by 55 feet. This arrangement uses 24 90-degree elbows, as well as a ball and check valve in front of the pump, and the associated head loss from these fittings was taken into account when analyzing the total head loss of the system. Another possible method of pipe installation is to arrange the loops vertically, but this installation costs become much higher, so a horizontal arrangement was chosen. 2 piping materials were considered for the ground loop: Schedule 40 steel pipe and PVC pipe. Both steel and PVC have a very similar roughness value, so the material choice will not have a significant impact on pump requirements. Steel has a much larger heat transfer coefficient than PVC, meaning that a shorter ground loop would be required to achieve the desired heat transfer rate. However, steel costs more than 2 times as much per foot compared to PVC. Both materials were input into the ground loop heat transfer MATLAB code utilizing the Hardy-Cross method. The total length of pipe required for each material was found. After running the simulation, it was found that PVC would end up being the most cost-effective choice of piping material. PVC also has the advantage of being corrosion resistant without any additional treating or coating.
This system requires a shell and tube heat exchanger that transfers heat between the ground loop and the refrigerant loop. This heat exchanger requires 4 tubes that are a length of 10 feet each that can handle a mass flow rate of 1,450 pound mass per hour. The heat exchanger has a head loss of 34.6 feet. This was determined using the Shaw method in MATLAB.
The pump requirements are driven by the volumetric flow rate of the system, as well as the head required to overcome head losses in the piping network and the heat exchanger. The required head is 103.8 feet, and the required flow rate is 2.87 gallons per minute. The pump chosen is a Flint and Walling 8-stage, half horsepower, 10 gallon per minute submersible pump. The performance curve was plotted in Excel, and a best fit curve was fitted. The resulting equation was included in the Hardy-Cross MATLAB code. This pump has an operating RPM of 2,400 and mechanical efficiency at 2.87 gallons per minute of 67%.
The heat transfer fluid used in the system is a 15% by mass propylene glycol solution, which is a mix of propylene glycol and pure water. This is because it is safer for humans and animals, it is environmentally friendly, and it has an anti-freezing additive. This anti-freezing additive is important because at a certain time of year, the temperature of the refrigerant loop could drop below the freezing point, which could cause a pipe to burst. This solution has a transfer coefficient of 0.484 watts per meter Kelvin, which means it has a loss of performance compared to just water alone, but it was deemed acceptable because of its benefits.
On this slide, we have a table that breaks down the cost of our system. For the PVC piping, we used Whitehead Industrial, which had a price of 26 cents per foot. For the 1,046 feet needed of PVC piping for our ground loop, the total cost for PVC came out to be $275.60. The 90-degree elbows that were needed, we purchased them from PVC Fitting Online for 34 cents each. For the 24 elbows, that came out to $8.16. For the shell and tube heat exchanger, we priced out the steel piping from Speedy Metals to be $87.76 for the 40 feet needed. The check valve would be purchased from Home Depot at $4.76. The ball valve, which is used as the shutoff valve for the pump, would also come from Home Depot at $3. The cost of the pump was calculated from Dean Bennett Supply to be $294. The propylene glycol was purchased from Amazon.com for 3.585 gallons. It came out to be $8.32. The installation was estimated from Home Advisor to be $2,500. The total cost comes out to be $3,181.60. In conclusion, our project was to optimize the ground loop of a geothermal cooling system. We accomplished this by utilizing different materials, pump selection, MATLAB, and antifreeze selection. The area of the house was 2,000 square feet. The total heat transfer rate was 11.716 kilojoules per second. The material for the ground loop was PVC. The ground loop length was 1,045 feet. The material of the heat exchanger was steel piping. Mass flow rate of the heat exchanger was 1,450 pound mass per hour. The pump model was a Dean & Bennett 4F10S05. The fluid solution was a 15% by mass propylene glycol, and the total cost of our system was $3,181.60.